All right, let's just jump straight into this explainer. Today, we're tackling an absolute classic, finding the Kth smallest number in a binary search tree. You know, whether you're gearing up for a brutal technical interview or you just want to flex those algorithmic muscles a bit, this problem is literally a perfect showcase of how truly understanding your data structure can completely flip your approach to solving a problem. So here's our core challenge for today. How on earth do you track down a single specific value hidden inside a massive, sprawling data tree without checking every single branch? Now, finding a value might seem super simple at first glance. You just look absolutely everywhere until you spot it, right? Well, doing it with maximum efficiency, without wasting precious computing power on branches you literally don't even need to look at. Now, that's where the real puzzle lies. We've got to be surgical about this.
Let's set our baseline here. We've got a tree made up of n nodes. Our constraints are pretty straightforward. N is at least 1, and our target, which we'll call k, falls somewhere right between 1 and n. So looking at this example, if we want the fifth smallest value in this entire tree, our goal is to isolate that exact node. And here, that happens to be 6. Keep this visual tucked away in your mind as we start mapping out our strategy.
Moving into section 1, the aha moment, unlocking the BST advantage. I mean, sure, we could just naively dump all these nodes into a standard array, run a quick sorting algorithm on it, and grab the kth element. Easy, right? Actually, scratch that. Doing it that way completely ignores the built-in superpower of our data structure. The absolute crucial point to remember is that a binary search tree is already inherently sorted. By definition, every single node's value is strictly larger than everything in its left subtree and strictly smaller than everything on its right. We literally do not need to sort the data because the tree has already done all the heavy lifting for us.
Because we're hunting down the absolute smallest values first, we've got to start all the way down at the leftmost node in the tree. That means we can toss out algorithms that look at the root node first. So say goodbye to breadth first search or pre-order traversal for this one. They're just not the right tools for the job. Instead, in-order traversal becomes our absolute best friend here. With an in-order traversal, we process the left subtree, then the current node itself, and finally the right subtree.
And this perfectly illustrates that path. Think of it like a journey. By recursively traveling down that left subtree first, you see that blue triangle representing everything smaller than our node X? We guarantee that we'll hit the smallest nodes first. Then boom, we hit node X itself. And finally, we swing over to the right subtree, that purple triangle holding all the greater values. Tracing this exact path is an ironclad guarantee that we're going to encounter every single node in perfectly sorted ascending order. Okay, on to section 2, the first milestone, the recursive approach. So let's look at how a recursive function actually builds this fully sorted list for us. Whenever it's called on a node, it follows a strict to-do list. Step 1, go grab the sorted values from the left subtree. Step 2, add the current node's value into the mix. And step 3, append the sorted values from the right subtree. By firing off these recursive calls all the way down to the very leaves of the tree, the function eventually bubbles back up, handing us a complete, perfectly sorted list. And once we've got that list, well, finding our answer is as simple as plucking out the value at our target index, which is just k-1. But hold on, we really need to talk about efficiency here, because this recursive approach has a pretty massive fatal flaw. Big O of n. Both the time and the space complexity end up being O of n, where n is the total number of nodes. Why is that bad? Well, it forces us to traverse and store every single node in the entire tree just to build that list. I mean, imagine you've got a tree with 1 million nodes, right? But your k is only 2. You literally only needed the second smallest number, but your code just processed and saved all 1 million nodes anyway. Talk about a massive waste of resources. Which brings us to section 3, the climax, the iterative optimization. Now let's hit the brakes on processing that entire tree and look at this direct contrast. You see, with a standard recursive depth-first search, stopping early is actually super annoying. It naturally just wants to complete its entire cycle. But if we shift gears to an iterative approach, where we manually manage the process using our very own stack data structure, we suddenly give ourselves a brand new superpower. We get the ability to pull the ripcord and exit the traversal the absolute exact second we find our answer. So how do we actually pull this off iteratively? Well, think of it like an explorer carefully mapping out a deep cave system. First, we dive as far down to the left as we possibly can, and we push every single node we pass onto our stack so we don't forget it. Once we hit rock bottom on the left, which is our absolute smallest value, we pop that top node right off the stack. Boom, we've just found the first smallest number. So we check off a box and decrement our target k. Now, if our k is 0, we're done. We stop right there, claim our prize, and return that node's value. But if not, we just pivot our attention over to that current node's right child and we repeat the whole process. The beauty here is that we only ever move forward exactly k times.
And finally, Section 4, the resolution, comparing the complexities. To fully appreciate the optimization we just engineered, we gotta look at the hard data. And this grid proves exactly why iteration takes the crown. Just look at that time complexity. We took it from a sluggish O of n all the way down to O of k plus h. Why the huge drop? Because we're only processing k nodes now. That little plus h you see, that just represents the tree's height. Basically the time it takes for our initial dive down to that bottom left node before we start counting. And check out the space complexity. Instead of hoarding all n nodes in memory, our custom stack only ever holds a maximum of h nodes at once. It's just a single branch from the root to the leaf at any given time. We literally just slashed our memory footprint.
All right, I want to leave you with one final kind of provocative thought to wrap up this explainer. We just established that our shiny new optimized time complexity relies pretty heavily on h, the height of the tree. But what if the tree isn't perfectly nicely balanced? Think about what happens to our highly optimized iterative solution in the absolute worst case scenario. Imagine a tree where every single node only has a right child, so it basically just forms one long straight line. In that scenario, the tree's height perfectly equals its total number of nodes. So I ask you, how does that structural breakdown end up affecting all that efficiency we just worked so hard to gain? Some to chew on. Keep exploring, keep optimizing, and hey, thanks for diving into this explainer with me today.